So here in example 2, where we have got a black fly population, and it's modeled by this particular equation. And so P is equal to 9,000 times 0.75 to the exponent T, where P is the population of black flies after T number of days. So we're going to graph this relation. So first off, we need to fill out the rest of the chart. Okay. So if T equals 0, my starting value, my initial value is going to be 9,000 insects. Okay. So then what I'm going to do is I'm going to carry on. I'm going to use the equation, and I'm going to figure out how many bugs or how many flies are left after 2 days, 4 days, 6 days, 8 days, 7 days, etc. So if I want to figure out how many it is after 2 days, I take 9,000 times 0.75 raised to the exponent 2. Okay, so that's going to give me 5,062.5. Then I'm going to do the same thing. I'm going to start off with 9,000 times 0.75. That 0.75 is raised to the exponent 4. That's going to give me 2847 point, call it 66. And I'll do the same thing. I've got 9,000 times 0.75. This time I'm going to raise it to the exponent 6. And that's going to give me 1601.8. Okay. And then 9,000 times 0.75 raised to the exponent 8 is going to give me about 901. And finally, I'm going to do 9,000 times 0.75 raised to the exponent 10, and that's going to leave me approximately 507. So I'm just going to quickly round things up, just because it's a lot easier to round it, because you can't have a half of a fly or a fraction of a fly. So what I'm going to do is, as I go through, I'm going to start filling out the graph. Okay, so one, I can tell you what the initial population is. The initial population is after 0 days. So after 0 days, the population is 9,000. Okay, so there are 9,000 flies after 0 days. So now I actually have to go by and I need to graph this. So after 0 days, and again, here I have days on the bottom. Okay, and I got number of flies at the side here. Okay, so I start off with 9,000 flies on the first day. On the second day, I have approximately 5,000 flies, a little bit more than 5,000 flies. On the fourth day, I have about 2,850. Oops, that should be over here. So on the fourth day, I've got about 2,850, and that's about mid-range. On the sixth day, I've got about 1,600. So that'll be around here, in this ballpark. On the eighth day, I've got 900, so a little less rather than 1,000. And on the 10th day, I have 507, so about down here. Okay, so if I want to go through and I want to graph this, I'm just going to join my dots together as smoothly as I can. I'm going to join my lines together. So now I've got my exponential curve. And so now what I want to do is I want to figure out what's the population at the end of the first week. Okay, well, the first week represents 7 days. Okay, 1 week is equal to 7 days. So I got to figure out the population after the first week. So what I'm going to do is I'm going to find the interception okay, of where that happens to be relative to my chart. So here's 7 days. 1, 2, 3. Okay. And so I could go through and I could figure this out. Okay. And I'm going to guesstimate based on my graph and my graph alone that it's probably around, call it 1300 or so. Okay. So based on my graph, then I can estimate that it'll be about 1300 from the graph. Okay. However, I also have the equation, and so what I can do, I know that P is equal to 9,000 times 0.75 to the exponent x. I know that 7 days is how much time I've got, so I can substitute in my 7 days the for the number of days. Okay, so I'm going to substitute in I got 9,000 0.75 to the exponent. That's supposed to be a 7. There, that's a much more legible 7. So now I'm going to go through and I'm going to plug this into my calculator. And I'm going to do, again, bear in mind that the base and the exponent, according to the rules of Bedmas, need to be dealt with first, okay? So we're going to put in 0.75 raised to the exponent 7 times 9,000, and that's going to give me approximately 1,201. Okay, so there should be about 1,201 flies at the end of the first week. So on my graph, because of human error and the fact that my graph is imperfect, I guesstimated it to be about 1,300 based on the graph. The formula is a lot more accurate, and so using the formula, I got a more complete and correct answer. And so my formula answer is 1201. Okay. So approximately how long will it take for the population to be reduced by 50%? Okay, well 50% of the starting number, we started with 9,000. So 9,000 divided by 2 is going to equal 4,500. So we want to figure out how long does it take for the population to hit 4,500. So again, if I go back to my graph, and I try and use my the graph that I've drawn, 4,500 would be about here. So I'm going to draw my line over, and now I'm going to come down. Okay, and so it's a little under 2.5, so I'm going to call it about 2.4. Okay, so it's going to actually be based on my graph. Okay, it's going to be about 2.4 days. So 2.4 days. Now, that's how you figure it out using your graph. There is, however, another way that you can do it that's even more accurate, and to do it, use something called a logarithm. And I'm going to quickly show you how to do that because I think it'll be really useful and it is a good time saver. And we use a logarithm anytime that we're trying to figure out an unknown exponent. Okay, so we don't know how many days it'll take, so we're going to try and figure out what our unknown exponent is. So in order to use a logarithm, do that over here. So I know that I'm trying to get a final 4,500. Okay, that's my final population. Okay, and I want to know when we get to that final population. So I'm going to plug in that population of 4,500 into the original equation. Okay, so I've got 9,000 times 0.75 to the exponent x. So I don't know what that exponent is going to be. So what I need to do is I need to isolate the power by itself. And again, the power is this piece right here. Okay, I need to get that piece all by itself. And in order to get that piece all by itself, I need to remove that 9,000. So in order to remove the 9,000, what I'm going to do is, because I have 9,000 times this power, I'm actually going to divide both sides by 9,000. So I'm just going to use some algebra here. Okay, and that's going to result in getting an answer of 0.5 is equal to 0.75 to the exponent x. Okay, so what I have here is I have my final answer. Okay, so this is my answer, and this is my power with the base. Okay, and so I've got my base as 0.75. Actually, I'm going to change that around. I've got I have my base as being right here. Okay, so in order to use the logarithm, what I need to do is I need to use, I'm going to change colors for this. I need to do the log of my answer divided by the log of my base is going to equal my unknown exponent. Okay, so it's going to equal my unknown exponent. So I'm going to substitute in my values. I know that my answer is 0.5. I know that my base is 0.75, and that's going to equal x, which is my unknown exponent. So on your calculator, there is a button called log. And so on my calculator, I need to press the log button and then 0.5, and then divide that by log of 0.75, and that spits out an answer of 2.41 approximately. Okay, so my graph was very accurate, but if you get into a situation where you don't have the graph, you can use a logarithm to figure it out by doing the log of the answer divided by the log of the base, and that will equal your unknown exponent.